Hi everyone. So today we're going to talk more about Gibbs free energy. And there are three different ways that we can calculate Gibbs free energy. So we'll go through examples of how to use each of these different equations or methods. So in method one, we use our derived equation for Gibbs free energy, which we saw previously. So in this reaction, the change in Gibbs free energy is equal to the change in enthalpy for the reaction minus temperature times the change in entropy for the reaction. And then in the second method, we're going to use an equation very similar to previous equations we've used for enthalpy and entropy. So we're going to use Gibbs free energy of formation for products and add them all together, and then we're going to subtract the Gibbs free energies of formation for the reactants. And then in the final method, we're going to add together Gibbs free energy values for a stepwise reaction. And this will be pretty similar to what we've done previously with enthalpy. So in the first equation, temperature can change, so we do have a temperature factor there. But you'll also notice we're using standard enthalpy and standard entropy values. So that's what the little degree symbol means. So degree equals standard. Now, remember from our last lecture, we talked about what standard means. So typically, under standard conditions, measurements are made at about 25 degrees Celsius. So let's just put in parentheses here, 25 degrees Celsius. And the pressure is usually 1 atmosphere, or the concentration is 1 mole per liter. Now, with Gibbs free energies, we're usually discussing gases, so we would want the pressure to be 1 atmosphere and the temperature to be 25 degrees Celsius. Now, even though the measurements for enthalpy and entropy in equation 1 are done at 25 degrees Celsius, they don't change that much with temperature, so the temperature can vary for that equation. Now, in equation 2, we don't have a temperature term in that equation, and you'll notice that delta G of formation is also under standard conditions, so 25 degrees Celsius. So that means that the second equation can really only be used if the temperature is 25 degrees Celsius. So up above, we said that temperature can vary, but down below in equation 2, temperature has to be 25 degrees Celsius. And then in method 3, we'll go through an example where we take a series of reactions and manipulate them slightly to kind of get an overall reaction. And then from that, we'll just add together all of the Gibbs free energy values for each reaction. So if you don't quite remember doing that in the past, that's okay. We'll definitely go over an example. All right, so let's start with equation 1, and we're going to go over an example using that equation. So one of the possible initial steps in the formation of acid rain is the oxidation of the pollutant SO2 to SO3 by the reaction shown below. So sulfur dioxide reacts with oxygen to produce sulfur trioxide. And we want to calculate Gibbs free energy of the reaction at 25 degrees Celsius and determine whether the reaction is spontaneous. Okay, so because this is at 25 degrees Celsius, we probably could have used equation 2 here as well, but we're going to use equation 1 just to get some practice. All right, so equation 1 is shown off to the right there. Now, first, we need to look up delta H values and delta S values for each of the reactants and the products. Now, we don't have delta H of a reaction handy or delta S of the reaction handy, so we're going to need to use some equations to calculate those. So that means that we need delta H of formation for each of the products and reactants, and delta S, so the standard molar entropy for each of the products and the reactants. So let's make a little table. So we'll put the molecule first. So we've got SO2, O2, and SO3. And then we'll look up delta H of formation for each of those, and we'll also look up the standard molar entropy for each. All right. Oh, I should probably include some units in there. So delta H of formation will be in kilojoules per mole, and standard molar entropy will be in joules per mole Kelvin. Okay, so in the appendix of your textbook, we can find the values for each of these different molecules. So the enthalpy of formation for SO2 is negative 296.8. The enthalpy of formation of oxygen is just 0 because it's a pure element. And then the enthalpy of formation of SO3 is negative 395.7. Now for standard molar entropy, the value for SO2 is 248.2. For oxygen, it's 205.2. And remember, for standard molar entropy, we always have positive values above 0 Kelvin. And then for SO3, the standard molar entropy is 256.8. Okay, so let's start by calculating delta H of the reaction, and then we'll calculate delta S of the reaction. And let's actually write out those equations. So delta H of the reaction is equal to the sum of the moles of each product times delta H of formation of each product minus the sum of the reactants. And then for delta S of the reaction, that's the sum of N times the standard molar entropy of the products minus the sum of N times the standard molar entropy of the reactants. And so we had actually used that equation in the last lecture. Okay, so this is going to be a bit of a long problem, but that's okay. We're getting some practice in. So let's start with delta H of the reaction, and we'll start with the products. So let's see, we have 1 mole of our product, and the value of the enthalpy of formation for the product, SO3, is negative 395.7 kilojoules per mole. And then we're going to subtract the sum of the reactants. So we have 1 mole of SO2, and its value of enthalpy of formation is negative 296.8 kilojoules per mole. Oh, my pen wants to write in bold, apparently. And then we need to add the enthalpy of formation of oxygen. So that's 1/2 times 0. So that would just be 0. Okay, so what we end up with is negative 395.7 kilojoules per mole plus, because we have two negatives, 296.8 kilojoules per mole. All right, so we actually end up with a value of negative 98.9 kilojoules. Oh, and moles canceled earlier, so we can actually get rid of that unit. All right, so this means that this is an exothermic reaction. So delta H is greater than or less than 0. Okay, so now the next thing to calculate is the entropy of the reaction. All right, so delta S of the reaction is equal to, let's start with the products. So again, we have 1 mole of our product, and its standard entropy value is 248.2 joules per mole Kelvin. And then we'll subtract the reactants. So we have 1 mole of SO2, and its standard entropy value is 205. Oh, nope, 256. I was looking at oxygen. Oh, sorry. Got distracted and clicked on the wrong thing. So joules per mole Kelvin. All right, and then we're adding the moles of oxygen. So we have 1/2 moles times 205.2. Oh, I ran out of room there, as usual. Okay, so if we put that all together, let me find my notes. All right, so let's just kind of simplify all of this. So we have 248.2 joules per Kelvin, because moles will cancel. And then we're subtracting 256.8 joules per Kelvin. And then we're also subtracting 1/2 of 205.2 joules per Kelvin. Okay, so if we plug that all into our calculator, we should end up with a value of negative 94.0 joules per Kelvin. All right, so delta S is negative for this reaction. And does that make sense with our reaction up above? Yes, because we start off with 1.5 moles of reactants and only 1 mole of product. So the system is becoming more ordered, right? So entropy is decreasing, so that makes sense. Okay, it's always good to just do those little checks to make sure that you have something that does make sense with our system. All right, now we can finally calculate delta G. So I'm going to rewrite our equation for delta G. And we can just plug in everything we know, but the temperature should be in Kelvin, and we were given Celsius. So let's just do a quick calculation. Temperature is equal to 25 degrees Celsius plus 273. So that is 298 Kelvin. Okay, So now we have everything we need. So let's plug in delta H. Although we also need to make sure all of our units are similar. So delta H was in kilojoules and delta S was in joules. So maybe we'll convert delta H into joules just to make everything the same. So delta H we calculated as negative 98.9 kilojoules, but let's just multiply that by 1,000 to put it into joules. And then we're going to subtract 298 Kelvin times delta S, which we said was negative 94 joules per Kelvin. Okay. So when we plug this into our calculators, we get negative 70.9 times 10 to the third joules. All right, so typically delta G is expressed in terms of kilojoules. So we can convert everything back to kilojoules. So let's convert negative 70.9 times 10 to the third joules into kilojoules. All right. So essentially here, 10 to the third joules will cancel and we'll get negative 70.9 kilojoules. All right, so delta G is negative, so it's less than 0. So is this a spontaneous reaction or a non-spontaneous reaction? So this is a spontaneous reaction. So if we look at delta S that we calculated previously, we said it was negative, which is technically non-spontaneous, but that was for the system. And remember, we said that sometimes the change in entropy of the surroundings can make up for negative delta S of the system. So delta S of the universe was still positive because delta G is negative. So it all works out. Okay, so now let's try using the second equation that we saw. Now, in the second equation, we're going to use standard molar free energies of formation. So the free energy of formation, delta GF, is the change in free energy when 1 mole of a compound forms from its constituent elements in their standard states. The free energy of formation of pure elements in their standard states is 0. So this is similar to enthalpy. So down below is a table showing different free energies of formation. So you'll notice that if something is in its pure elemental form, it has a delta G of 0. Oh, and also included in that is graphite. And then everything else has either a negative free energy or a positive free energy, depending on the delta G of formation, and whether it's spontaneous or non-spontaneous. Okay, so let's use that second equation we saw on the first slide to solve the following problem. And we're also going to use the free energies of formation from that table. So ozone in the lower atmosphere is a pollutant that can form by the following reaction involving the oxidation of unburned hydrocarbons. So if methane reacts with 8 moles of oxygen, we end up with carbon dioxide and 2 moles of water and 4 moles of ozone. Use the standard free energies of formation to determine delta G of the reaction at 25 degrees Celsius. All right, so previously we said that ozone was a good thing, right? It is a good thing in the upper atmosphere, but if we have ozone kind of at our level of the atmosphere that we're breathing in, ozone can be bad. It is considered a pollutant at lower levels of the atmosphere. All right, so we're going to use this equation shown here. But first, let's look up all of the delta G values. So let's make a little table again. Okay, so let's see, CH4, we'll start with that. And if we go back, CH4 has a value of negative 50.5. And then O2 is a pure element, so that will just be 0. CO2, let's go back. That is right here. So that's negative 394.4. And then H2O gas, let's see, that's right here, negative 228.6. And finally, ozone. Let's see, is ozone in here? Oh, no, ozone is not in there. I do have the value, though. I think in the back of the textbook, if we look it up, its value is 163.2. Okay, so now we have everything we need to calculate delta G of the reaction. Oh, I did not give myself an extra slide. So, all right, if you have these values in your notes, what I'm going to do is just erase this table we made. I didn't plan ahead very well. Okay, so now let's calculate delta G of the reaction. All right, so we'll start with products. So let's start with CO2. We have 1 mole of CO2, and its delta G value is negative 394.4 kilojoules per mole. And then the next product is H2O, and there's 2 moles there. And its delta G of formation is negative 228.6 kilojoules per mole. Oh. And then oxygen, or ozone. It's easy to get those two mixed up. So that is 4 moles times 163.2 kilojoules per mole. Okay, and then we're going to subtract the reactants. So here, let me actually extend the brackets around the products. So everything in that upper portion is products. And then for reactants, we have methane, CH4, and there's just 1 mole. And its value is negative 50.5 kilojoules per mole. And then we have oxygen, which is just 0, so we have 8 moles times 0. Okay. So let's add up everything in the products first, because that will help us kind of simplify all of the math here. So if we add up everything in the products portion, we should get negative 198.8 kilojoules. And you can pause the video at any time if you want to double check the math. And then if we add up everything in the reactants, we should get positive 50.5 kilojoules. So overall, the Gibbs free energy of this reaction is negative 148.3 kilojoules. All right. Now, the question didn't ask if this was a spontaneous reaction, but is this spontaneous or non-spontaneous? So delta G is negative, so this would be spontaneous. All right. So now let's go over the last method. So again, in the last method for calculating delta G, we can take a series of reactions in a reaction mechanism, and we can manipulate them in order to get to the overall reaction. But when we do that, we also have to manipulate the delta G of reaction for each individual step. So if a reaction can be expressed as a series of reactions, the sum of the delta G values of the individual reactions is the delta G of the total reaction. Now the reason that we can do this is because delta G is a state function. So it really just depends on the initial state and the final state. So this is similar to enthalpy and entropy. All right, so when we're manipulating our reactions, let's say we have to reverse a reaction in order to get to our overall reaction. We also need to change the sign of delta G for that reaction. So if a reaction is reversed, the sign of delta G reverses. And then if the amount of materials is multiplied by a factor, we also have to multiply delta G by the same factor. So for instance, if we need to multiply a reaction by 2 in order to get to our overall reaction, then we also have to multiply delta G by 2. So delta G is actually extensive, which means it depends on the amount that is present. All right, so if none of this is making sense, don't worry, we'll see this process in action. All right, so let's do a practice problem. And again, all of these problems are in your textbook, but we're just going through them together so you can kind of see how they work. So let's find delta G of the following reaction, where 3 carbon atoms react with 4 molecules of hydrogen gas to produce propane, C3H8. Now this reaction actually involves 3 different steps. So we have 3 different reactions shown below, or rather this doesn't actually involve 3 different steps. It's more so that we can use these 3 different reactions and their delta G values to get to the delta G value of the reaction. So in your textbook, there should be delta G reaction values for these 3 different elementary-ish steps. So initially we have propane reacting with oxygen to produce carbon dioxide and water. So that's a combustion reaction for propane, and that has a known delta G value. And then we can also use a second reaction where carbon reacts with oxygen to produce carbon dioxide, so that's a combination reaction. And that has a known delta G value. And then we can also use the combination reaction between hydrogen and oxygen to form water, which has a known delta G value. So using these 3 different reactions, we can manipulate them in order to get the original reaction that we're interested in. All right, so let's rewrite each of these a little bit larger. Okay, so this first reaction, if we're trying to end up with our overall reaction at the top, we want C3H8 to be in the products. So that means we need to flip or reverse that reaction. All right, if we reverse that reaction, we also have to change the sign of the delta G value for this reaction. So delta G would be positive 2074 kilojoules. All right, now for the second reaction, we have carbon reacting with oxygen to produce CO2. Now we want carbon to be in the reactants according to our overall reaction, so we don't have to flip this reaction. However, we do want to end up with 3 moles of carbon. So what we'll do is multiply this whole reaction by 3. But if we multiply that whole reaction by 3, we have to do the same thing to the delta G value. So we'll have 3 times negative 394.4 kilojoules. Okay. And then the last reaction, we have 2H2 plus O2, which forms 2H2O. Now, hydrogen gas is in the reactants for our overall reaction, so that matches what we have here. But we want 4 moles of hydrogen gas, not 2. So let's multiply this whole thing by 2 so that we end up with 4 moles of hydrogen. But that means we have to do the same thing to the delta G value. So 2 times negative 457.1. Okay, so let's rewrite all of these so that they reflect the manipulations that we've done. All right, so our first reaction, we just flipped it, right? So this would be 3CO2 plus 4H2O reacts to produce C3H8 plus 5O2, and the delta G value is positive, positive 2074 kilojoules. All right, and then the second reaction, we multiplied everything by 3. So we had 3 carbon plus 3 O2, which reacts to produce 3 CO2. Okay, so we multiplied the delta G value by 3. So that would give us negative 1,183 kilojoules. And then in the last reaction, we multiplied everything by 2. So now we have 4H2 plus 2O2, which produces 4H2O. And we also multiplied delta G by 2, which gives us negative 914.2 kilojoules. All right, now let's just double check that we do end up with the overall reaction that we were trying to achieve. So what we're going to do now is cancel anything that appears in both the reactants and the products. So looking at our reactants and products, I do see 3 CO2 on the left and 3 CO2 on the right. So those will cancel. And then I do also see 4 H2O on the left and on the right, so those will also cancel. I also see that we have 5 O2 on the left and 5 O2 on the right, so those will cancel. And everything that's left over is what we want. So let's write our overall reaction. So on the left of our arrow, we have 3 carbons and 4 hydrogen molecules, and we're producing propane. All right, so that matches what we saw up above, which is perfect. And now we just have to add together all of our delta G values to get the overall delta G of our reaction. So we're going to take 2074 and subtract 1183 and then subtract 914.2. So we should end up with negative 23 kilojoules for our delta G of reaction. So is this a spontaneous reaction or a non-spontaneous reaction? So delta G is negative, so it is spontaneous. All right. So hopefully that helped a little bit. These stepwise processes are a little complex. So more often we would probably take this reaction up here and use one of the other two equations, especially if we're at 25 degrees Celsius. This process, it's a little cumbersome, so I would probably use methods 1 or 2 instead. Okay. So next time, we're going to talk about Gibbs free energy under non-standard conditions. So far we've been assuming that everything is under standard conditions, but there are situations where maybe the pressure isn't 1 atmosphere, or maybe the concentration isn't 1 molar, for instance. So we'll talk more about delta G under non-standard conditions next time. So I will see you then.